Hi there and welcome to Mastering V-Ray, Lesson 2, Materials 101. This video will be structured a little bit differently to the first video, as we're now beginning to deal with both technical and creative decisions. The video will be broken into two parts, theory and practical, and I'll begin by explaining some of the fundamental laws real-world materials exhibit, then show you how to implement those laws using layered V-Ray blend materials. As this video is meant to be an introduction to the material creation process, I won't be covering advanced topics yet, such as procedurals or texturing. However, you will have a solid understanding of how to create accurate metals and plastics based loosely on real-world data taken from refractiveindex.info. I owe a lot of thanks to many members on the forum over the last year, but none more so than John O'Connell. As the only person probably more interested in materials than myself, I'd like to thank you for helping me overcome a few of the hurdles I faced in understanding this material stuff and for solidifying some of the unanswered questions myself and the community has had. I'd also like to thank Peter Guthrie for providing the Sky HDR seen in this video. There'll be a link in the PDF attached to the video directing you to his new site where you can purchase some of his other HDRs. So once again, thanks to all of the people who helped me get this far. I really appreciate it, and I'm looking forward to seeing what you guys can come up with using these techniques. A couple of you have already sent me some examples, and it's looking really promising. So we'll get started with part one, and that's theory. Thanks. So when creating materials, traditionally the most important aspect to consider has always been the Fresnel value. And you'll no doubt remember going through those long lists online trying to find that correct number to plug into this Fresnel reflection slot here. The problem I found is that that simple numerical value doesn't do a good enough job of describing the way most materials reflectivity works. So the very first thing to understand when creating materials using this approach is that we won't be ticking this Fresnel reflections box. Instead, we'll be creating it with a fall-off map and a custom curve for our reflections. It can be a little bit overwhelming trying to understand what different materials' reflectivity curves look like, but thankfully it can be broken down into two separate categories, and they are metals and plastics. So before I jump into Photoshop and show you some slides and examples of what different Fresnel curves look like, I'll just show you how we're going to be creating our own custom Fresnel values. So in the reflection slot, just make a fall-off map. You can leave it at perpendicular and parallel. And if you tick the enable color map, you can see now we've got a little graph here. If you tick a little plus box, we can add our own little point. And here we can begin to create a fall-off curve on the reflection. If I bring this example up, you can see now as I raise or lower it, the reflectivity changes. So an interesting thing to notice is that you can reproduce the default value of 1.6 just by going in here and bring this up just a little bit. Sorry, we've just got to untick the Fresnel. So you can see that changing that value more or less reproduces exactly what's happening with the default Fresnel value. If I change that to 3, go back into this material, all I've got to do is just kind of raise it up a little bit. And you can see it matched. So I'll just stop there and show you what actual values look like. So what you're looking at here is two different Fresnel curve examples that I've taken from the Cornell University website. On the left you can see a generic metal Fresnel curve, so something like typical aluminium, and on the right you can see a generic plastic Fresnel curve. Now the actual values you see in these graphs aren't as important as showing the difference in reflectivity between these two materials. As you can see, the generic metal material maintains a very high reflectivity regardless of the viewing angle. However, the plastic material behaves quite differently. You can see here as the viewing angle increases, the reflectivity starts to ramp up, but not until about 40 or 50 degrees. For those who don't understand what these graphs are showing you, it's quite simple. All you're seeing is the material's reflectivity in relation to the angle in which you are viewing it. So on the right here we've got the angle from normal, and vertically we've got the reflectance. So let's take a look at this effect in real life. So what you're seeing here is an approach I developed while I was at Electric Art when I was trying to understand how materials behaved based on the viewing angle. So basically what I did was I opened up a high contrast texture on my iPad or iPhone and placed it directly behind the object or material I was viewing, and observed what was happening as I saw it closer and closer to the grazing angle. Now, it's definitely a rudimentary approach and by no means scientifically accurate. However, it does do a good job of showing the Fresnel effect, as well as another more important feature of complex materials I will get into in just a minute. So let's start viewing it from different angles and see what happens. You should go back and replay this part a few times, but ultimately you can see as you view the Wacom surface at different angles, the reflectivity changes also. And it changes in a way that very closely resembles the plastic Fresnel curve we saw in the earlier graph. So now that you understand that reflectivity changes based on viewing angle, you need to observe how reflection glossiness changes based on viewing angle also. This second material feature is ultimately the reason you bought into Mastering V-Ray, as it's been a very hard and costly effect to reproduce in any 3D package. Thankfully, this video is going to break it down for you, but before I do that, let's take another look and I'll point out the effect to you. So in this first slide, you can see the reflection's extremely matte. There's no mirror quality finish to the material. You can't read anything in the Mastering V-Ray. In the second slide, it's still pretty much the same. Extremely matte reflections, no visible detail in the circle or the Mastering V-Ray text. In the third slide, we can finally start to see that the glossiness of the material starts to get a bit higher towards, maybe like 0.8 in V-Ray. At extremely grazing angles, we can see that there's visible mirror-like finishing, and there's like checker detail. You can see the Mastering V-Ray. And finally, in the third slide, where we're almost at 90 degrees, I had to basically be underneath the table to see it from this angle. We can see that there's a very high mirror finish quality, but at the same time, it's still a little bit glossy. So it's this important feature in materials that we're going to create now, and ultimately what's going to make your materials look a lot more realistic. So as you know, the bidirectional reflectance distribution function describes a material's glossiness. But what you might not know is that there are two different kinds of BRDFs currently being written: simple and complex. Unfortunately, at the moment, V-Ray only has simple BRDFs, and as you can see, it means they aren't capable of producing multiple specular lobes. To simplify things for the average user, what it means is that the glossiness spreads uniformly regardless of viewing angle. However, what we just observed on the Wacom surface paints a very different picture of what's actually happening. This next image shows you the difference between a complex BRDF and a simple BRDF. On the left and right, you've got V-Ray's standard BRDFs. You've got Blinn and Ward. And in the center, you've got the custom one we're going to be creating next. And you can see that there's a non-uniform glossiness distribution as opposed to the Ward and Blinn, which is just the same throughout. So it's this center effect that we're trying to produce. So let's go back into Max now and get on creating it. Now that you understand the basic theory behind complex materials, I'll begin by showing you how to create a simple layered plastic material. As I've created so many now, I don't often need the real-world data to determine a material's reflectivity. I mean, it becomes a pretty repetitive process eventually. However, during this initial learning phase, I've got to go through everything for you. So it's always good to know you're sticking to like actual physical values. The best place to obtain that information is at refractiveindex.info. So if I just go there now, you can see what the page looks like. Now there's a couple of important pieces of information I will describe when we advance to making colored metals, but for now I'll get you to swap to plastics in the drop-down menu. Change the material to polycarbonate and set the wavelength value to 0.55. Now that number is an average of the red, green and blue wavelength numbers that make up most complex metals and stuff like that. But for now that value of 0.55 is good enough to represent simple materials that don't change color based on the reflection angle. So for plastics, this is all you need to worry about as they aren't complicated. Alright, so once you put that in, scroll down the bottom here and you'll see that there's a reflection calculator section. Now this graph here has all the information you need to reproduce the Fresnel curve of this polycarbonate material. So looking at that, one of the things you can do here is you can save out a JPEG of that. So if you just click here, save a JPEG, you don't need to go back to the website, so while you're in Max you can just have that image there. You can see it produces this graph here. So if we go back into Max, this is the graph that we're going to try and reproduce in the reflection slot, and we've got all the information here to do that. So like I said earlier, we're just trying to reproduce the green line here. Now it might be a little bit confusing to see this S polarized and P polarized and non-polarized line. Basically the green line is an average of the red and blue lines. They're just different methods of capturing the reflectivity of a material, and neither are perfectly accurate, so they just average the two, and all you need to focus on is this green gradient. I was a little bit confused originally. I thought it was the red, green and blue wavelengths, but it's not. It's just all you need to worry about on that site is the green curve. So in here, let's go back to that original plastic we were creating. Fresnel's been unticked, and in the reflection slot, you can see we've got a very wrong reflection curve here. So go back into this JPEG image, and we can see at 40 degrees the curve is still pretty much flat. So we know here, if we go in this slot, if we set it to 0.4 here, we need to level that out. And if we look at the reflection map again, at 70 degrees, we're at 0.2 reflectivity. And you just do your best to match that gradient. Another bit of important information you need to match is the initial starting reflectivity, and you can see it's about 0.06 or something like that. So just go in here and input that. So there you go, there's the reflectivity of a polycarbonate plastic. Now that we've matched the reflection curve, we need to go in and create a layered material to reproduce the glossiness based on the reflection angle. It's best to just render off what we've got so far. Before I do that, I'm just going to swap to a more yellow material. It just makes it easier to visualize the reflection. So just set it to 25 and 255, 255. Just going to render that. Every time I do a test render, I'm just going to pause the recording just to make things a lot quicker. So if it skips, just you'll know why. So now that that's rendered, the next step is to make this into a V-Ray blend material. So click here, make it a V-Ray blend material, and keep the old material as a sub-material. And now you've got your base in the base material slot. We're going to duplicate that into the coat material slot. So drag that over, make it a copy, just change it to plastic coat 1, any naming convention that you're used to. And now we've got 2 layers. You can see the value, the reflection glossiness value in this base material is 0.6. Now we want to get, as we get towards the 90-degree angle, we want that glossiness to go up. So I'm going to make this 0.8. You can see that changes the material preview. But we need to blend based on the viewing angle. So what I'm going to do is I'm going to copy that reflection map and paste it into the blend amount. Now we want this to blend kind of 50% with the original base coat. So this curve is going to look different to the reflection fall off curve. Unfortunately, there's no real world data, or there's no website like Refractive Index that will give you that glossiness value. So we kind of just need to eyeball it. So for this initial video, just using some rough values here, and if you slide that up to 0.5, you can see now that we're blending the glossiness based on the angle. So it's going to be more matte on the facing angle, and as we get towards the edge, it's going to be more glossy. The problem with only using 2 layers in the material is that you don't often get a very nice gradual transition between a matte material and a highly mirror finished material. The problem is I don't like the slow render times of using three materials in a blend, but sometimes you've got no choice. For plastic, you can probably get away with just 2 layers, but to demonstrate the realistic approach to this, we're going to go in and make another layer, and that last 3rd layer is going to be the mirror finish layer. So drag it over again, and now from 0.8 we want to change that glossiness to 0.99, and you can see it's producing a mirror finish. Just rename it. Just got to rename the base. And we can copy that glossiness blend amount curve. And we only want this top coat. You'll notice if you look at the Wacom surface again, you'll notice that that mirror finish is only appearing at very, very grazing angles. So we need to blend this representing that. So go down to 0, slide this curve in a little bit, and then drag it out. So what this new blend amount is telling us is it's only going to use that mirror finish material on these far grazing angles. So now we go from 0.99 glossiness down to 0.6 based on the blend. So I'm just going to do another render of that and show you the difference. I'm just going to save this initial render in the history. And I'll re-render. Just going to set this new one as A and B so we can compare the two. Now if I slide between them,